Phenols can be represented by AROH, or this structure here. The oxygen in OH is sp2 hybridized because this oxygen is right next to a carbon that is sp2 hybridized. One of the lone pairs will occupy the p orbital. Examples of phenols are naphthol, this is an intermediate in making dyes, and L-DOPA. L-DOPA is a drug for Parkinson's disease. It has 2 hydroxyl groups. Phenols are much stronger acids than alcohols. Bases can remove this proton to produce the phenoxide. Phenols are much stronger acids because this negative charge can be delocalized to the ring and shared with other atoms. Delocalization increases the stability of the phenoxide. Here are a series of phenols, and take note, phenol has a pKa of 10. If you put a methoxy group at para position, methoxy group is an electron donating group. It will donate electrons and counter the delocalization of this negative charge. So it has a negative effect on acidity. Chlorine is an electron withdrawing group. It can pull electrons towards itself. This negative charge can be pulled further from oxygen, so that acidity will increase. A nitro group is also electron withdrawing, and whether it's at meta position, it has a strong inductive effect and also can pull electrons towards itself. Thus, the acidity will decrease. The best effect will be a nitro group at the para position. It can readily form resonance structures. It has resonance effect and also inductive effect. And so this negative charge on oxygen can be distributed properly to several atoms. Thus a pKa that is relatively lower and a compound that is more acidic. Phenols are soluble in aqueous sodium hydroxide. pH of aqueous sodium hydroxide can be around 12 to 14. At this pH, most alcohols are insoluble. Most phenols are not acidic enough to be soluble in aqueous sodium bicarbonate. Aqueous sodium bicarbonate has a pH of about 8 to 9, depending on the concentration. Carboxylic acids are soluble in aqueous sodium bicarbonate. Why do we say these generalizations? It has something to do with pKa. The determination of pKa in water follows this equation. That when you put your acid HA in water, it may dissociate to form its conjugate base A- and the hydronium ion. An organic acid may have low solubility in water, but if it becomes its conjugate base, it has a negative charge. A negatively charged species tend to be more soluble in water. So if you have more negatively charged species, solubility will increase. To understand the implication of this equation further, we need to know these relationships. These relationships are discussed in analytical chemistry, but you will need to know this to understand our topic. If pH is lower than pKa, then the concentration of your HA must be higher than the concentration of your A-. If pH is equal to pKa, the concentration of your HA is equal to the concentration of A-. If pH is greater than pKa, then the amount of A- should be greater than the amount of HA. It means that if the pH is higher than the pKa of the substance will dissolve easily because there are a lot of A-. A- is more soluble than HA. So if you have an organic acid such as phenol, alcohol, or carboxylic acid, Solubility will depend on the pH. Take note that phenols have a pKa of about 10, so if the pH is higher than 10, such as when you have aqueous sodium hydroxide, then phenols will dissolve. Alcohols have a pKa of 16, and this is higher than the pH, so there will be more alcohol than the alkoxide, and alcohols will be less soluble in water, except for low molecular weight alcohols, of course. On the second bullet here, most phenols are not acidic enough to be soluble in aqueous sodium bicarbonate because the pH of aqueous sodium bicarbonate is 8 to 9. The pKa of phenol is about 10, so there will be more of phenol than the phenoxide. The pKa of carboxylic acid is about 4, and if it's mixed with sodium bicarbonate, then you will expect that it will be deprotonated, and there will be more of the carboxylate, the negatively charged species that is present in solution, so carboxylic acids are expected to be more soluble in aqueous sodium bicarbonate. How are phenols prepared? One of the most common methods of preparation of phenol is called the Dow process. It involves heating of chlorobenzene with sodium hydroxide under high pressure, and you will get a reaction in which your chlorine is substituted by a hydroxyl. The mechanism here is not nucleophilic aromatic substitution. If you are interested, several books in organic chemistry discuss that mechanism. Another method is melting of benzene sulfonate with sodium hydroxide. It is a process that is so similar to this first one. You just replace this chloro group with sulfonate and high temperature and high pressure as well. The last one is using cumene hydroperoxide to produce phenol and acetone. The preparation of cumene is already discussed in another video about aromatic compounds. In the presence of oxygen and heating above 100 degrees Celsius, you will produce the cumene hydroperoxide. Mixing in acid at this temperature can convert it to phenol and acetone. Phenols react by electrophilic aromatic substitution. They are strongly activating and they are ortho para-directors. Usually a tribromide is obtained if you use bromine water. Nitration using 20% nitric acid has low yield due to competing ring oxidation. And sulfonation gives ortho product at low temperature and para product at high temperature. One interesting reaction of phenols is called the Kolbe reaction. Kolbe reaction involves intense pressure and temperature with carbon dioxide and sodium hydroxide. You will get this compound here, and acidification will give you this compound. Further modification by acetic anhydride in the presence of catalytic sulfuric acid will give this compound. This compound here is more popularly known as salicylic acid, and this compound here is the drug aspirin. Phenols can be oxidized by reaction with Fremy salt or potassium nitroso-disulfonate to yield a quinone. This is potassium nitroso-disulfonate. You have a phenol, and upon this reaction, you will produce a quinone. Hydroquinone undergo mild oxidation to p-benzoquinone. Possible reagents include chromium trioxide, sodium dichromate, and hydrogen peroxide. This is hydroquinone, and it will be oxidized to p-benzoquinone. Once you have your benzoquinone, it can be reverted back to hydroquinone by tin chloride.